For the longest time, technology was something that lived on our desks or maybe in our pockets. But that's all changing. The next big thing, it isn't about tinier screens or faster chips. It's about tech moving from out there to in here, right into our bodies. We're talking about a serious merger between human and machine. So let's jump in and see what that future could actually look like.
And this isn't science fiction anymore, not really. This is the central question that's driving this whole field of human augmentation. We're talking about technologies that could let us overcome our biological limits. I mean, what if we could give a factory worker superhuman strength, or allow someone who is paralyzed to walk again?
So, right now, there are kind of two parallel paths developing. On one hand, you have what we're calling external helpers. Think of wearable robotic exoskeletons that you literally put on. And on the other hand, you have internal links. These are tiny, incredibly sophisticated implants that connect directly to our nervous system. Let's start on the outside, and then we'll work our way in. All right, first up, robots we can wear, also known as exoskeletons. Now, you've probably seen these in movies, right? But their most promising real-world use right now is actually in industry. For jobs that demand a ton of repetitive, heavy lifting, these devices are being tested to see if they can make work safer and just less physically brutal. The promise here is huge, and it goes way beyond just lifting more weight. We're talking about AI-powered exoskeletons that can seriously reduce the biomechanical load on a worker's spine, potentially preventing those career-ending injuries. They can cut down on fatigue, which keeps people safer and more on the ball during a long shift. And ultimately, if you lower the physical toll of these jobs, you might be able to help companies keep their experienced workers, who might otherwise have to take an early retirement. So that's the promise. A future with fewer workplace injuries, a workforce that feels more supported. Sounds great, right? Well, when these amazing devices leave the clean, controlled lab environment and get put onto real people doing real jobs, a very different story starts to unfold. And this slide just lays out that disconnect perfectly. Real-world studies show that the number one barrier is, get this, just plain physical discomfort, pain, pressure, and heat from wearing the device all day. Next up is poor ergonomic fit, which is a huge issue, especially for women. Then they actually restrict movement. It all points to this fundamental problem. A device might be great at reducing strain in one specific motion, but if it gets in the way of every other little thing a worker has to do, its overall value just plummets. This quote from a worker who was in a field trial, it just says it all. "I did not feel pain in my back, but the exoskeleton was hindering me." So the device did its main job, right? It prevented back pain, but it completely failed at the bigger picture. It got in the way of the actual work. This challenge, this task incompatibility, is a massive hurdle. It really shows the tech has a long way to go before it can just seamlessly blend into our lives. Okay, so now let's shift gears. We're moving from technology we wear to technology we implant. And this is where things get way more personal, and the potential for life-changing results becomes, well, even more profound. We are literally talking about plugging directly into the brain and the nervous system. And just so we're clear, this is not some far-off dream. It is happening right now. In what is an absolutely landmark achievement, researchers have successfully used a wireless interface to create a bridge over a damaged spinal cord. The system basically reads the intention to walk from the brain and then wirelessly zaps that signal to a stimulator on the spine. It bypasses the injury and restores natural movement. It is just a stunning, stunning breakthrough. The tech that makes this all possible is called a brain-machine interface, or a BMI. Put simply, it's a bridge. It decodes the electrical signals of your thoughts and translates them into commands a machine can understand. And that machine could be a prosthetic limb, a computer cursor, or even another part of your very own body. It's a closed loop between thought and action. And the innovation in this field is just exploding. Scientists are creating these ultra-thin electrodes that can allow someone with a prosthetic hand to actually feel what they're touching. They're also building bioresorbable electronics. Think of them as temporary implants that can help a nerve heal and then just safely dissolve. No need for another surgery to remove them. And maybe the most incredible of all, they're developing these things called neuromorphic sensors that have AI built right in so they can spot the onset of something like a seizure right at the source in real time. So, we've got these two incredible paths, right? Powerful robots on the outside and these super intelligent sensors on the inside. But for all their differences, they are both running smack into the exact same fundamental roadblock, the human body itself. This chart tells a really interesting story about where the research focus is for exoskeletons.
Out of 49 real-world studies, a whopping 37 of them were in industry. Meanwhile, healthcare got only 10, and social care, a field with huge physical demands, got just 2. It kind of suggests that we're prioritizing industrial productivity over the more complex, messy, human-centric needs you find in fields like medicine and caregiving.
And this comparison here makes that shared problem crystal clear. For exoskeletons, it's about poor fit, discomfort, even social stigma. For implants, it's a mechanical mismatch with our soft, flexible tissues, which can kick off an immune response from the body. You see the pattern? In both cases, the rigid technology is kind of fighting against the very biology it's supposed to be helping. Now, beyond all the physical challenges, there's another less visible problem that unites both exoskeletons and implants, and that's the massive amounts of incredibly personal data they collect. What happens to that data? Well, that is a huge and largely unanswered question. You would probably assume that any data coming directly from your body is protected health information. But in the US, the reality is, well, it's a confusing patchwork of laws that were never, ever designed for this kind of technology. So what this means is that there's no single sheriff in town for your bionic data. The HIPAA law, we all know, a lot of the time it doesn't even apply to the company that made the device. Instead, the FTC might regulate it as a consumer product, while the FDA only gets involved if it's being used for medical diagnosis. So a single data point could fall under 3 different jurisdictions, creating huge gaps where your privacy and security could just fall right through. So with all these incredible promises and all these very real problems, how close are we really to this augmented future? Well, let's take a look at a kind of roadmap for these different technologies. Okay, so using this scale called Technology Readiness Levels, or TRLs, we can see a pretty clear progression. Things like those dissolving implants, they're still in the early stages, mostly lab research. A bit further along, you have flexible probes for brain mapping. Those are being validated in preclinical trials. And then at the most advanced stage, you have those amazing brain-machine interfaces for paralysis, which are already being evaluated in early human trials. But even with our most advanced technologies, biology always pushes back. Look at this number. Our best brain implants can lose over 15% of their signal quality in just 6 months. And why? It's simple, really. The body's immune system sees the implant as a foreign object and tries to build a wall around it. This signal drift is a fundamental biological hurdle we still haven't figured out how to solve. And that right there brings us to the core takeaway of this whole explainer. Whether we're building a robot to wear on our back or a sensor to place inside our brain, the biggest challenge isn't making the technology smaller or smarter. It's making it compatible with a soft, dynamic, messy, and just brilliant system that is the human body. Which leaves us with one final and much, much bigger question. As these external helpers and these internal links become more and more a part of our lives, they're not just changing what we can do, they're changing what it means to be human. And that is something we all need to be thinking about.